Good afternoon, everybody, and thank you for joining us from all around Australia. I hope everybody's staying safe out there. My name's Matt Hunter, and I'm the Innovation Technology Product Manager at Konica Minolta Australia. Some of you may already know that Konica Minolta have been supplying 3D printing equipment and services into the Australian market for about 5 years now. We've helped educators, we've helped manufacturers, we've helped the healthcare industry and the defence industries to adopt this innovative technology. We've been proudly representing 3D Systems here in Australia for that whole time. And I guess today we wanted to share some information with you around, I guess, the hugely popular 2500 platform. I think it's its material range and accuracy that makes it a really versatile platform. So we'll be really interested to just share some information with you around that this afternoon. With that, I'd like to introduce our speaker today from 3D Systems, Sam Green. If you've attended any of our other webinars over the last short period of time, you may have seen him on a previous one around the Figure 4 platform. Sam's worked in the development of additive manufacturing solutions for 10 years, specialising in DLP and resin jetting technology. So a wealth of experience to share with us here in Australia. Before I hand over to Sam, just quickly, feel free to use the Q&A section. We'll try and answer as many of the questions as we can at the end of the session. With that, I'll hand over to Sam for his presentation.
Thank you very much, Matt. So as Matt mentioned, before we dive in, quickly, my name is Sam Green. I'm the category manager for the professional line of 3D printers at 3D Systems. I've been involved in additive manufacturing for about 10 years now, and I've worked in some of the largest 3D printing system vendors in the industry, with most of my experience being with resin jetting technologies such as MJP. Today, I'd like to talk to you about a number of new indirect manufacturing applications that you can achieve using what we call multi-jet 3D printing, and in particular based around the Multijet 2500 plus 3D printing system from 3D Systems. Along the way, we'll review a little bit about the basics of this technology, and then we'll get into some good examples of those indirect manufacturing applications. So let's get started. So for those of you not yet too familiar with MJP technology, I've tried to summarize here the main benefits, and we'll elaborate on some of these points as we go through the presentation, but I wanted to provide, at a glance, what this technology delivers. So first of all, it's highly accurate parts with the finest design details that actually I've ever seen from a jetting technology over the years, and I've seen quite a few. Of course, any printer is only good as the materials and the 3D parts that come out of it. So material development is key, and 3D Systems is constantly working to introduce new materials, advanced engineering materials, and we'll see a few examples today that open new application possibilities for manufacturers, designers, and engineers. Unlike other technologies, MJP is really ideal for producing what we call moving assemblies straight out of the printer, for lightweighting otherwise heavy parts. You can simulate glass or PMMA with a range of clear transparent materials, and functionally you can simulate a lot of parts such as snap fits, hinges, and you can create very strong jigs and fixtures. The parts also large enough to fit a good majority of the industry applications, and I think lastly, MJP is just a fast 24/7 uptime type system that is today used by many hundreds, many thousands of design and manufacturing companies, small scale, medium scale, large enterprise, you name it, in virtually every manufacturing industry in the world. So that's a brief summary, a lot there to swallow, but let's look at some of these in more detail now. So, and of course, we'll tie in these details and see how they tie into indirect manufacturing as we go through. So we mentioned that MJP delivers the finest design details. So what is so special about MJP technology in this regard? So MJP stands for multi-jet printing, and it uses inkjet print heads that jet an acrylic-based resin that's cured by UV light as it hits the build tray. Now, this uses proprietary thermally controlled materials. As each of the heated droplets of material is jetted, it immediately cools and holds its shape as it lands on the part or the support surface. Now, this is not necessarily the case with other resin jetted 3D printers. With MJP materials and the technology that we've developed, the material droplets do not ooze over the edges or pull in corners, and that's what I've tried to demonstrate in this with these two diagrams here. So the edges, the result, and this is of course important for any of the design parts that you're printing. The edges with MJP technology are typically 90 degrees sharp. The holes are round, the corners are clean, and the sidewalls have excellent overall quality. Now combine that information to the actual printer resolution. So the 2500 system prints at 800 by 900 by 790 dpi at 32 micron layers. And just for a general non-3D printing world comparison, the human retina has a limit of just 300 dpi. So we're talking about 800 to times 900 times 790 dpi. So well beyond what the human retina can discern. And accuracy is plus or minus 0.001 to 0.002 inch per inch of the actual part dimension. And as you can see, the result here in this comparison, I've put here an MJP part at the top, in the top diagram, and a non-MJP part, or a typical leading competitor. And you can see this is a shower jet nozzle, and a real close-up, a really good close-up that we could get of the actual holes in the nozzle itself. And you can see that with the MJP parts, those holes remain triangular, perfectly triangular, all the way up to the very tips, while the competitor tips actually become sealed about 3/4 of the way up. And the result of that is that you can see the spray of water coming out of the MJP nozzle at the top here, and you see that spray is straight and clean, the way it's intended to be by the manufacturer, while the competitive prototype is very skewed, and that's a nice test or an indication of the resolution of the part. Another factor responsible for delivering fine design details, something that is often overlooked when you're choosing a 3D printer, is the support material. Now, this is where jetting technology differs from other technologies such as SLA or DLP or FDM. Jetting technology allows you to separately jet a model material for your part and then a differently formulated support material that will end up being washed away or sacrificed in the process. So MJP technology has really perfected this process of jetting a support wax that is easily dissolved away in a hands-free process that also doesn't use dangerous chemicals. So this process takes care of the very fine details of the parts. And because we're not using heavy chemical-based solvents or high-pressure water jets like we'd find in alternative jetting technologies or systems out there, so there's no damage or deformation to the part. And you can see I've put a comparison here. This is MJP, a part with internal geometries and fine holes at the top. And you can see there's been no damage to that fine meshwork of holes. The part remains, the shape is dimensionally stable and correct, whereas when you're using different support technologies that are not so easy to remove, you either have to blast them away with a water jet, and that would break some of the fine details in the support, in the structure itself, or you'd have to use a chemical sodium hydroxide, which can end up deforming the part, as what's happened in this lower diagram here. And here's just a typical part that I've printed and filmed for you in my own hand. You can see the holes on this filtration device are clean of support material. They're very sharp, unlike other jetting technologies, and the curved surface is smooth without any stepping effect or visible build lines that you typically get even from high-end FDM type printers. So as I mentioned, we're constantly working to improve and expand the material possibilities available on the MJP platforms. To date, we have a range of general purpose materials in white, clear transparent, gray materials, So that's the VisiJet's M2R white, M2R clear, M2R grey. These materials feature standard rigid functionality with a moderate flex and a look and feel of injection molded plastic parts, and they're good for typical prototyping applications. We have then the M2R clear and white, which are class 6 capable for medical, biocompatible, and skin touch applications. And then we have the tan material, which is really a really nice high contrast material with a good modulus and a heat resistance up to 71 degrees C. Then we have the M2R black, a rigid black material, which is highly rigid, low flex, as well as a higher temperature resistance and an opaque black finish. Then we move more into the realms of engineering materials. We have what's called the VisiJet Armor, which is the M2G Clear. This is an engineering clear material, which has a really great strength combination of tensile strength and flex, delivering advanced prototyping performance for many applications, and we'll see a few here today. We have the VisiJet ProFlex, which is the M2G Dura. This is another engineering material, more similar to a polypropylene-like performance. So it's great for living hinge type applications and use cases that require durability and extreme pliability. And then we have some elastomers. We have the M2 EBK, which is an elastomeric black, and we have the and then a natural colored elastomer of the same type. And these are excellent for printing soft rubber-like parts like gaskets, piping, and some types of molding applications. So in these two GIFs here, I printed just a couple of nice parts and tried to film them for you close up. So the left part here is printed in the M2R rigid black material. So what's great here is that the part features a functional screw thread assembly that came like this out of the printer itself. And that's thanks to the soluble support and the high fidelity and resolution of the printer itself. And then you see the part on the right. This is printed in that tan material that I just mentioned to you. Again, this was printed as a finished assembly, and it comes out of the printer smoothly working with accurately printed, fine detailed joints and hinges. And again, both these parts are the type of parts that would be ideally printed in MJP technology, both in terms of the moving parts and the complexity and the final quality of the parts themselves. Okay, so in this slide, you get the ultimate pleasure of seeing me in person. Here I am. I printed one of my favorite parts, actually. This is a part that is, and this is a capability that's really unique to MJP. This is actually the body of a commercial drone. Using the 3D print software package that comes with the printer, you can quickly and automatically create a sparse, hollow structure within your parts. And with the excellent soluble support capability that we have and some cleverly located drainage holes, you can end up with a part that's up to 70% lighter, but almost as strong. And of course, with less material, you cut your cost per part down, in this case, by up to about 35%. And of course, you can see this part, I'm throwing it up in the air. You can see that it's significantly lighter than typical resin parts that tend to be very, very dense. This is actually a great use case, and I didn't show all the parts here, but we also printed the blades of the drone, you know, the helicopter type blades. And again, using other vendors, they wouldn't be able to do both the blades of the drone and the body of the drone using the same technology. They'd have to use two different technologies. Typically, they'd use something like maybe an FDM device to produce the body of the part and lightweight it, and then they'd have to use a jetting technology system to create the very fine blades, which need very smooth surfaces and fine details. But again, in using MJP, you can produce both the body and the blades using the same printer, which I think is a great use case here. Another important feature of MJP technology is the ability to produce clear, transparent parts. And we have a choice of two basic clear materials. That's the VisiJet M2R Clear, which, as I mentioned a few slides back, is a biocompatible class 6. This is really a great choice for medical devices when you need skin contact or mucosal membrane contact, and where you need to see through the part, such as when you're creating surgical guides or devices where liquid or gas is being tested through a system. The second material is a VisiJet armor, which I mentioned to you, that's one of our engineering materials. This is a great functional material when you need high impact resistance for simulating parts that would be part of a larger assembly, such as an automotive lighting cover or electrical or consumer goods products. The parts can also be tinted with regular fabric dyes to create a nice selection of clear or colored parts, as you can see in the bottom photograph here. Out of the printer, the clarity typically does not look exactly like these parts you see in the top diagrams. These are after sanding and lacquering, but that is a fairly simple process. You could do both sanding or lacquering or just one of the two, or to create a real glass or PMMA-like simulation to your end parts. MJP technology is an excellent way to test complex, fine detailed snap fit designs. Stress concentration, stress relaxation, fatigue. I mean, these are all difficult design considerations for most snap fit designs. So the VisiJet armor and the ProFlex materials were specifically designed to create robust snap fits, simulating the properties of traditional injection molded plastics. And you can see this is a nice example of a snap fit part here produced in the armor material, and you can see what it looks like close up. So the details that are still captured on that spring and that hinge are nicely captured in the MJP technology. The rigid material is also extremely versatile for when you need to drill or tap holes or press fit precision dowel pins, add screws to bosses, press fit brass inserts, or even machine precision holes. You can also print the screw threads themselves directly within the part. The unique capabilities of MJP allow it to be, you can easily print most thread sizes, which can be used in combination with standard threaded machine screws. Now, this is not the case with other jetting technologies, in my experience. Typically, when you're creating jigs and fixtures, a lot of those basic materials tend to split or deform when you're trying to connect them with metal parts in a jigs and fixture assembly. Okay, so this is a nice little stop motion that compares the MJP 2500 Plus system on the left and another jetting system on the right. Both have the exact same parts on the build tray. The 2500 Plus system finishes the job in just 1/3 of the time. In fact, there are many jobs where it's just as quick or nearly as quick to produce multiple parts using the MJP as it is to just produce one part. And that's because the printer really runs along 3 lanes, if you like, based on the width of the actual print head. So the print head is roughly 1/3 of the size of the print tray. So it runs on 3 imaginary tracks, if you like. If you're able to stack your parts, or what we call nest them nicely within a single lane, you can become far more productive on large or recurring jobs. In fact, with a print speed of 303 cubic centimeter cube per hour, most practical jobs will be finished in 1 day or overnight on the MJP 2500 Plus. Add to that, the time and labor that's saved in post-processing, as I described earlier, and the easy job submission using the 3D Sprint software, and overall you'll be extremely fast and efficient compared to other systems and technologies. So that's just a brief summary of the benefits of MJP technology. Now let's look at what's new. For the start of 2020, well, we're mid-2020 now, but since the start of 2020, we've added some unique material capabilities that open some new and very exciting applications, both for prototyping and manufacturing, particularly with the use of 3D printing for indirect production parts. Now, essentially that means that you can now short circuit the expense and time needed to make tools that you would typically use within the traditional manufacturing workflow. So you can now make those tools faster and more cost effectively. So indirect manufacturing, just to explain a little bit, but I would contrast indirect manufacturing with direct production parts. Direct production is where a 3D printer is being used to totally replace your traditional manufacturing setup and workflow. And to be clear, that's not what we're talking about here. That's a discussion for another time. We do have solutions that answer direct production parts, but we are talking here about indirect manufacturing, which is using 3D printing to assist the traditional manufacturing workflow. Back at the last Formnext, gosh, it was a long time ago, the end of 2019, we introduced a new breakthrough in engineering materials, and that was the M2S HT90 material that you see on the right-hand side here. This was the first in a new line of advanced engineering materials. And just a couple of weeks ago, we introduced these other two materials that you see here, the M2S HT250 material on the left, quite similar to the HT90, but with an industry-beating 250 degrees HDT. And also the M2E BK70 material in the middle. That's a new black elastomer with a really good performing compression and memory. Also note here, all three of these materials are standard biocompatible class 6 rated, and I believe this makes us the only jetting resin vendor to introduce so many high performance engineering materials that are also biocompatible in one go. So let's take a closer look at the HT90 material and what this means for indirect manufacturing. So the HT90 combines 4 really useful properties and features within a single competitively priced material. First, we have its water clear transparency. When you sand and polish this material, it looks like perspex or glass. This is great when you need to view a liquid or gas flow within the material, or when you're trying to align a part over holes or screws. Secondly, it has a heat deflection temperature of 90 degrees C out of the printer, and that's with no additional post-thermal curing required. Remember, that's typically what other printers or other technologies would use in order to reach a higher HDT. They would need to put the parts in a thermal oven, and this would, as well as taking extra time from the entire time to part, it can actually lead to warping of the parts themselves. So this is 90 degrees C with this material straight out of the printer. Third, the HT90 is printed in a new ultra high definition printing mode. So this gives you even sharper planes than I mentioned before, even better corners and edges and details with virtually no appearance of visible build lines on the part. And fourth, of course, as we mentioned, the material features USP Class 6 biocompatibility for skin contact and mucosal membrane contact, making it ideal for medical devices or medical planning, as well as a range of parts that have to be worn on the skin. So how do these benefits translate into the traditional manufacturing world? That's the essential question here. Well, I've listed here just an initial sample of what these potential applications could be. But the message I want to get across here is that there may be quite a few more than what you see here, and they may be very specific to your unique business or industry workflow. But my intention is that you see just a few examples, and then you start to generate ideas and find ways to apply the same benefits of these, of our materials and technology to your own manufacturing setup. So let's take a look at some of these in a bit more detail now. First up is thermoforming. So this is one of those manufacturing processes that intuitively can benefit from 3D printing. The process consists of heating a thermoplastic material to a pliable temperature and then stretching it onto a molded shape. So of course you can use 3D printing for to create that molded shape and save time and allow designers and engineers to quickly and easily fabricate more complex designs that would be quite difficult using traditional technologies. They would require a CNC machine expert as well as your CAD designer. However, 3D printing, those dies are faster to generate, and they're sometimes cheaper compared to traditionally manufactured one-off or low-volume dies, and yet they can be used to form tens to hundreds or even thousands of parts, depending on your specific design. So using the new HT90 material, which is ideal for most thermoforming applications, the dies or tools can be used to replace either the entire machine die or just a small part of the die, which could be the insert in a larger traditionally manufactured die, right? The 90 degrees HDT provides a good thermal resistance to the hot plastic that contacts the tool. There's virtually no degradation to the tool during the process, and the 3D printed part provides a good cycle time for most geometries. So thanks to the fine feature definition of the MJP process, you get over 1.1 billion drops of material per cubic inch of part volume, which means you get really accurate and fine resolution dies or mold surfaces. Another great benefit is that the soluble support material allows you to create porous lattice structures and tiny venting holes for the vacuuming of the final plastic. In the example in the photos here, you see the top photo, we have a mold die printed in the HT90 material. From this part, 400 plastic parts were generated, 100 of them from each of the 4 tools that you see in the top diagram. And there was no noticeable degradation to the quality of those parts over the course of producing those 400 parts. The HT90's material elongation of break is between 4 and 9%, and that provides just enough flexibility to allow for the removal of those final formed parts from the dies without damaging the die or destroying the small features on the die surface. All in all, using the 3D printed tool and the HT90 material in this use case saves anywhere between ×3 to ×10 of the cost and time of traditional low volume tooling. So that's quite a significant time and cost saving. Second up, injection molding, right? So you can use the MJP technology with the new HT90 material, and similarly, you can save between 3 and 10 times the time and cost of traditional metal tooling in this case. So, so 3D printing can be used in 3 ways in this case. First, you can churn out fast production plastic injection mold tools for low volume jobs. Secondly, for creating unique high value inserts that sit inside the traditional molding tool plates. The inserts themselves are smaller compared to the full size tool, and you'd only have to undergo fractions of cycles compared to the main tool usage. And thirdly, for prototyping and thereby assisting in your development of those traditional metal tools. So iteratively testing metal tools for injection molding can typically take weeks or months. When you 3D print those prototype tools, you allow the designers to go through multiple iterations, modifications, design cycles, before investing in those final metal tools themselves, which are very expensive. For all of these applications, the HT90 offers the 90 degrees HDT, which is suitable for most thermoplastics with an operating melt temperature of between 140 to 200 degrees C. This means that you can typically injection mold plastics like polycarbonate, polypropylene, ABS, acrylic, PVC, and some other plastics as well. As we mentioned before, the elongation of break of 4 to 9% gives you the flexibility to bolt these tools securely into place, and also to remove the final injected parts without breaking the tool. Excuse me. And that fine feature definition, 1.1 billion drops per cubic inch of the part, allows you to create and maintain even the smallest details of the parts that you're actually intending to inject. And similar to thermoforming, of course, the soluble support and the 3D Sprint software that comes with the printer allows you to create those porous lattice structures, air venting holes, or even text on screen that can be legible, or text on the part, sorry, that can be legible and help you identify the different tools and the different customers they're going to. In this nice example in the photographs, we have polypropylene parts. They were injected at 176 degrees C at 250 psi barrel pressure and 1,800 psi core pressure. 25 molds were actually created. That's 4 sets of parts per print tray. Each mold succeeded with 10 to 15 roughly injected parts. So in total, 400 parts were manufactured in just 75 hours at a cost of around $100 per mold set. So that's a significant time and cost advantage compared to the traditional method that could take weeks for the metal toolings to arrive, and which would typically cost thousands to create those metal tools themselves. And that's great if you need a small batch run of in this case, 400 parts at low cost. A third use case, this is sheet metal forming. Typically in this process, a laser or water jet is used to cut out a flat die pattern, and then that flat pattern is bent and formed into the final desired shape. One of the main uses for 3D printing is in the creation of the embossed or formed features in the sheet metal die. These features are typically complex and unique, and therefore there's no general machine for such needs. Our tests show the 2-inch thick flat part of the armor material. This is one of the original engineering materials, not the HT90, but this is a great general purpose engineering materials. You can subject this material to between 10 and 15 tons of force numerous times without fracturing. So the mold, and you see the mold here in the top diagram between those two metal plates, the mold would always return to its true shape and could continue to be reused time after time in this particular case. So that's 10 to 15 tons of force being applied to the 3D printed part. Also, the transparency of the armor material and the ability to add screw threads to the design all assisted in the manufacturer, helping him to align and mount the parts correctly, saving time and material. The last thing you want is these parts to crack when you're trying to screw them into place, and then you have to start your printing process all over again. In this example, 3 MJP armor tools were used to make 300 parts between the jaws of these aluminium plates in the hydraulic press that you see here. No degradation to the part quality was experienced during the process, and the entire process turned around within just a few short hours, saving time and money, of course, compared to the traditional process. And this last example, this is room temperature vulcanization or silicon molding. You can use 3D printing in 3 different ways here, I would say. The first way is that you replace the silicon molding process altogether with a 3D printed eggshell mold. This replaces an 8-step traditional process with a 2-step process. An example is in the top photo here. Using the HT90 material, you create an eggshell mold, and then you inject that with the silicone, and the silicone part is the blue camera cover that you see that's come out of that. Method 2 replaces the 8-step silicon molding process with a 2-step process again, where you 3D print the actual silicon mold using an elastomer instead of the silicone. And for this, you could use the Multijet black or natural color M2 elastomeric materials that I introduced to you at the beginning. And those are quite good for printing soft rubber-like parts. And then method 3, where you 3D print the master pattern only, and that's what you see in the far right-hand diagram here, those 4 little parts. And you just 3D print the master pattern, and then you continue with all the regular 7 steps in the traditional silicon molding process. So some examples of these, as I mentioned, the far right corner here, you can see these 4 parts here. And of course, as in the previous examples, the same material properties are advantageous here. You know, the combination of surface quality, fidelity, dimensional accuracy, material stiffness, strength, elongation, all of those features work together to make any of these methods more timely and cost effective. In this example, in the bottom photograph here, we actually created a functional prototype of a rubber cap that is used to seal one of our own print heads in one of our own 3D printers. So in this case, a 4-piece mold was printed for around $200, and it was delivered overnight. And this process enabled our own R&D team to trial a true elastomeric part in the machine, and then to tweak the design repeatedly until the rubber injected part was a perfect design for the printer itself. So this process, of course, we're using it to create our own 3D printer, but it saved us weeks, maybe even months of development time, and of course thousands of dollars compared to CNC or metal tooling those tools. So I just want to switch gear just for a second, talk a little bit about COVID. It's still a hot topic. There are still many countries, looking to deliver medical equipment and there may be limitations on supply chains by OEMs. So one of the most critical pieces of equipment that we found, especially early on in the COVID crisis, was those medical ventilators. One clinical example was seen in Italy back in March, and this actually hit a lot of the main press. There were a group of people, they prototyped and manufactured 100 valves over the span of one weekend to help a hospital in a town called Chiari. In particular, the so-called Venturi valves, and this regulates the oxygen flow actually inside the ventilators. These valves were in short supply, and the OEM providers were not able to provide them in time. So in this situation, a local company in Italy called Isinova was able to reverse engineer those valves and print 100 of them with the help of their own 3D printer. Now, the parts were originally created on an extrusion platform, an FDM system, but then a 3D Systems customer of ours called Lenati, they actually own an SLS printer, the SLS Pro X 6100, which is one of our top-of-the-line SLS systems. They actually printed these parts in medical-grade nylon, and they were able to print many more. They were now much more functional and watertight than the original FDM parts. Of course, the correct course of action is always to check with the manufacturers first, but if the valves are not available, only in the case of a confirmed emergency, typically they'd contact a 3D printing service provider and produce a replica, and only then, of course, with certain conditions. But what's interesting is that we also reproduced those same Venturi valves, this time on the MJP 2500 system in the new HT90 material. Of course, there are many systems capable for doing this, including also our Figure 4 technology with its own high-speed medical-grade materials, or the Pro X SLS 6100, which is an SLS printer I mentioned, which would print these parts in medical-grade high-strength nylon materials. But the MJP system is ideal for when you need, again, complex parts, and that melt-away support material that we talked about is really ideal for supporting the building of internal flow chambers and voids, where the easy post-processing allows you to completely remove that support and not have any remaining residue left inside the part. And you can see that very small opening where you connect a tube to this part. You can see that would typically get filled with support material and not be so easy to remove in using other technologies. But in this technology, of course, MJP is perfect for producing that very small nozzle there and making sure the support removal is completely completed. So in this particular photo, 88 parts were printed on the MJP build tray in just 29 hours, and then 176 parts were post-processed in under 2 hours using our Easy Clean steam system, followed by a convection oven. So most of the time taken was in melting the bulk support material away, while most of the labor was just using soap and water to remove the final residue. Overall, the process amounted to about 30 seconds, or maybe just a little bit more than 30 seconds per part in terms of post-processing. And that's, again, 176 parts post-processed in under just 2 hours. Just a quick legal note here on this particular use case. As mentioned, this was an emergency situation where the OEM could not meet a critical demand. Whatever you print for COVID, your devices or parts need to be printed in an ISO certified facility, whether that's a hospital or a service provider. You also need to work with your clinical partner to validate the device and process. If not, then you may be liable. So I've tried to use the HT90 material as an example of the great variety of production-related applications that you can now achieve using additive manufacturing when you have the right printing technology combined with the right material chemistry. And of course, HT90 is just one of those 3 new advanced materials that we've introduced recently. This is the HT250 material. It provides a similar opening to a range of new applications, functional prototypes, tooling in hot environments, electronics and housing cases, thermal shielding and insulation, direct contact with melted solder material, for example. And if you know anything about solder, solder can be is typically molded at around 480 degrees C. You can actually create mold tools in this material that can contact the solder, and heated gas and liquid flow tests for engineering and medical applications. I've just put a nice little diagram that I received yesterday from a colleague. You can see here, this is a heat fan. It's really, really tiny. You can see the tip of the pen, so you get an idea of scale. These are 200 micron feature details on this part. And this is quite remarkable for a jetting technology. This is not something that I've seen that you can replicate using other jetting technologies at this cost and feature price point. So this is a beautiful part. And then let's talk quickly about the new functional elastomer material. That's the M2E BK70. This has been designed to really hit the sweet spot for most design and prototyping parts in the real world. Remember that most commercial elastomers tend to have a shore A flexibility of between 60 and 70 shore A. So this material has a shore A hardness of 70. What's really unique about this material is its compression set. So that's the permanent deformation that would remain after removing a strong force to the part. In this case, the permanent deformation is just 1 to 3%. Now, when you compare this to other elastomer materials that are 3D printed, it's really a world of difference. I've seen parts where we did the standard compression set test with other elastomers, and those parts totally collapsed under pressure, and they literally turned to what looks like a paste when you compress them hard. But the M2 EBK70 material exhibited no change under pressure. It has an excellent rebound, or what we call a memory speed. So that is another disadvantage of many 3D printing elastomers, that they tend to rebound very slowly. So they don't really behave like a true elastomer or a silicone. But this material has a better elastomeric memory speed, making it far more realistic for prototypes. And overall, when you combine the compression capability with its ability to spring back nicely, it's a great material for simulating gaskets, seals, bumpers, treads, grips, handles, and other types. And of course, this again is a biocompatible USP Class 6, so it's ideal for skin contact or mucosal membrane contact, as we mentioned. So there you have it, a number of real and practical use cases showing how MJP technology, in combination with some of the world's most advanced engineering material chemistry, can be used to improve the efficiency and effectiveness of traditional manufacturing processes. So if I could just summarize in 3 points, 3 things to take away, it's these. It's that MJP technology, it continues to be the world's most versatile technology for both prototyping and now indirect manufacturing. Secondly, that our material range, as you've seen, is constantly expanding and improving. So we're adding more and more value to those printers through advanced materials. And those materials are going more into the realms of high temperature and functional engineering performance. And that, the application of 3D printing can, at the end of the day, save you weeks and months of real product development time. It will improve your final product outcome through more iterations, and it will deliver cost savings between 10, sometimes even hundreds of thousands across multiple departments, whether it's your design department, your engineering department, or your production manufacturing floor. And of course, MJP technology and MJP, the 2500 plus system that we've been talking about, of course, these are just part of a much wider additive manufacturing portfolio offered by 3D Systems, which covers multiple technologies from resins to plastics to metal to inspection and design software to professional services. And at that point, I will stop here and hand it back to you guys and see what questions you have.
Great, thanks, Sam. It's really appreciate your time. A great presentation. A couple of questions. So, obviously, with your experience in DLP and SLA technology and jetting technologies, Why? What considerations would you have when you're choosing one versus another? And why would you choose one over the
Yeah,
other?
it's a great question. It's a great question. There's so many different advantages and disadvantages.
Yeah.
I think, I mean, if we just take SLA, for example, SLA is the original stereolithography. That's the original 3D printing technology. It was actually invented by 3D Systems. But SLA is great when you need large, long parts. I mean, the build trays on some of our systems go up to about 1.5 meters in diameter in the XY dimension. So one of the great advantages of SLA technology is that you're using a laser, of course, so you're able to achieve consistent levels of fine detail resolution and accuracy across the entire dimension of your part. So if you're looking for long, flat, fine detailed parts that are typically used in automotive applications, for example, and you want to ensure that there is consistent accuracy across the entire part, SLA is a great system to use. I think some of the disadvantages of SLA may be a bit slower than some other technologies. Other advantages of SLA, the parts, the clear materials on SLA are really, really clear. I think you get the clearest parts in the industry, the most transparent parts in the industry come out of SLA. I think MJP is a great all-round technology. Because it's a jetting system. It's relatively fast, it's relatively robust and simple to use. You've got, you're able to jet different materials onto the build tray at the same time, and that's really where it differs from SLA. SLA, of course, it's a single material in a vat of resin that's being, selectively scanned and lasered. But the MJP allows you to jet different materials. So the wax, the wax support, as I've mentioned, allows you to create complex internal geometries that can be easily cleaned out once that part comes off the printer. And I think that's one of the major benefits of MJP as opposed to other technologies out there. You also have DLP, right? Or it's other vendors call it DLP. We call it projector-based imaging or figure 4 technology. And this technology is really like a subset of SLA or an evolution of SLA. Instead of a laser, it features a projector. And instead of vectoring that image into the resin in a vector dimension, it does it in a layer by layer dimension. So the parts come out of a figure 4 printer much faster. You get very high print speeds, up to 100 millimeters per hour. But of course, it's like SLA. You're using a vat of resin. There's no separate support material, so there is a limit to to the internal chambers that you can achieve. I think that's the main differences in those technologies.
Yeah, I mean, I think you raise a good point. Just the gentleness, I guess, of the support removal, and in particular when you're talking about something that has very fine detail or internal channels, is as a huge advantage, I think, of using that multi-jet technology. It's a good segue into a couple of the other questions that are coming in, and they're around that finishing process. And probably two things here. One is how do you remove the parts from the build chamber? And I guess by expanding on that, we spoke really briefly about that finishing process. If we could just recap on what that is, and then a good point to make, and I think you made it during the presentation, is that hands-free finishing. And I think that people often overlook the fact that there's still time and labour potentially involved in the post-processing of a part. So talk a little bit to how the parts are removed in that finishing process, if you.
Yeah, I mean, first of all, we have a great post-processing guide for MJP technology on our website. It's free for everyone to access. You can go there and just download, or you just read it through. It's a great little document. But basically, very simple, hands-free process. You take that build tray with the parts still on it. Your print job is finished. You put them in a fridge or a freezer for a few minutes to harden that wax support. Make sure the parts are really cool, and then you can easily just snap them off of the build tray very easily and very quickly. If you want, you can use a little tool, a little scraper to help lift those parts off. But most of the parts can be easily removed once you put them in a fridge for a few minutes. They easily come off that build tray once that support is and the build tray have cooled down. So that's how you remove them off the build tray. The support material, as I mentioned, is a wax. 65 degrees C, it melts away. So we have two general solutions. You can either put it in a steam bath or a convection oven. Both processes will remove most of that support. For the fine remaining layer of support, we recommend using our Easy Clean system or mineral oil. Standard mineral oil. This is not any chemical, heavy chemical. This is a standard mineral oil, similar to cooking oil, and you simply put the parts in what similar to a chip chip net, and that mineral oil will dissolve away the final remaining support, and then you just take them out and wash them gently in mild soap and water to remove that final mineral oil. But as I mentioned, this is, most of this process, or a lot of it, is hands-free, especially removing the bulk of the support. It's mainly just the fine parts, the remaining support that is the manual part of the process. And this is very different. I mean, I remember myself printing parts using a different technology to MJP, where I would have to take every single part to a massive water jet system, right? You'd have to put those parts in the water jet, you have to put the rubber gloves on, and then you have to start blasting each and every single one with a high pressure water jet to remove the support. And guess what? In about 30 to 50% of cases, those parts would end up breaking because of the high pressure of the water jet. You angle it just a little bit wrong and the part will fly out of your hand and it will break inside that water jet machine. Very frustrating. Just a long process, very time consuming. And I think this process is just much cleaner, and just overall really a joy to use. Yeah. What was the second part of your question? Yeah, did I answer it all?
I guess the point, you have. I mean, the point I guess that I think is an interesting one is the point you make around having to individually finish a part as opposed to batch processing the finishing of parts. And I guess that's a massive time saver and a reduction in labour costs when you're looking at processing numerous parts. Couple other questions. So how hard is it to change materials? You spoke about a lot of different materials. How hard is it to change between one material to the next?
Plug and play. Not difficult at all. I mean, it's a cartridge-based system. Yes. It's not a vat of material that you need to pour away. You have an automated function on the printer that will purge the remaining material out of the jetting system, out of the tubes, and you simply take out the old cartridge and place in a new material. It's simple as that.
I think to extend on that a little bit, I think that's what makes it quite a nice office-friendly kind of device. And that's probably one of the points when you compare it to maybe SLA, for instance. Couple of other questions that are coming in. One is 2,500 parts sterilizable, and I think probably when you have a look at the high temperature parts and the class 6 nature of them, then that would be absolutely yes. Obviously, there's a few different methods of sterilization, but the most common method, I think, would be heating with steam, right?
Yes, so both the HT90 and the HT250, because they're HDT and biocompatibility, can be used in the standard autoclave sterilization process. Those Venturi valves that I showed you earlier, that's how they're post-processed. They go through the sterilization process as well. So I think the high HDT and means that those parts end up as they are out of the printer. There's no significant deformation due to both the humidity of the sterilization process or the temperature of the sterilization process.
It's great. While we're on materials, do the resins have a shelf life? If so, how long?
Yeah, I believe, don't quote me, I believe it's a year or 2 years.
Actually, I could probably help you out there. Yes, it typically is 2 years, and then depending on the material, there is a process to actually extend the life as well. That would be backed by Konica Minolta. In the future, do you see a stronger multi-jet material that can be used for end-use parts?
Mm-hmm. That's the holy grail of any jetting technology. Look, I think we're getting there. First of all, with these parts, obviously the inherent trade-off of any resin, 3D printed resin, is that you trade high temperature for brittleness, right? So at the function of a production material is a combination of impact resistance and temperature resistance. To be very simple, you want to combine high toughness, high impact resistance. Something over typically 50 to 70 joules per meter would be really good. That's in the realms of what we call ABS plastics, and you want an HDT typically above 60 or 70 degrees C. Anything beyond 100 or up to 100 is fantastic. So we have managed to reach the HDT requirement of production, but of course with acrylic resins, as the HDT goes up, the brittleness of the parts also go up, and that is the real challenge. How do you achieve a high HDT without sacrificing the impact resistance of the part? We're working on it. I think we've demonstrated these parts today. They can be compressed under 15 tons of pressure without cracking. They can be used in multiple jigs and fixtures and with metal inserts without breaking under that pressure. So we're approaching the realms of production, I believe. Indirect production is the first step to direct production. If you do need real production parts now, I think our Figure 4 technology, which I mentioned earlier, is groundbreaking. We have materials such as the Pro Black 10, a number of materials, and also elastomers that are true production capable materials. Another of the challenges of resins is that they are cured by UV light. So what happens is when you take them out of the printer and you use them in the open sunlight, they continue to cure, and they actually overcure with time, and that's what leads to deformation and brittleness of the parts if they are exposed to years of usage, in regular UV conditions. And of course, humidity adds to that because there is some water absorption. So the combination of humidity and sunlight does affect resin parts as a general rule, but we're working on that. And just the Figure 4 technology, for example, we've created a number of production materials now that are UV stabilized. That they do not deform in UV light, they do not deform under humidity or heat. They can be used outside applications for up to 3 years, and they can be put in storage for years as well. So we're getting there with some of our other technologies, and I believe we will get there with MJP as well.
Yeah, I think interesting there that there are, I've come across applications where people are chroming or painting those parts, and obviously that extends the UV life of the part as well.
Absolutely, yeah. Good point.
Yeah, the other interesting point I think is, when you talk about end-use part, well, exactly I guess, yes, there is end use part, as you described, it's the final part that's going to be used. But I actually think that augmented manufacturing, is also a valid end use part, right? A jig or a fixture or a pattern is still an end use part, right? So it just depends on the context around that as well. So an interesting one. A couple of other questions here before we close off. I know we're kind of at time, but what size is the build envelope for 2500? I think it's 295 by 211 by 142. That's millimeters. And then any multi-jet materials food safe? Not something I've had much to do with, to be honest. Do you know, Sam, of any applications that's used it in that way?
I would have to look into that.
Yeah, okay.
I haven't come across anything specifically, so I would have to check. I believe it's a different class, right? I mean, we have class 6 biocompatibility.
Yeah.
I think food safe is a different class number. I would need to check. Let me check and get back to that one.
Thanks, Mr. Anonymous. You've stumped us on that one. But one thing we have come across here in Australia is actually we have taken MJP parts and Teflon and managed to Teflon coat them. It still remains to be seen whether that would qualify it as food safe, but probably worth investigating. I got one other question, and this is an interesting one, and probably something that we didn't quite touch on in this presentation. I think this is probably a webinar all on its own. But how widespread is the use of MJP in the jewelry industry? And in fact, there is a specific 2500 that is used to print in a jewelry casting wax. I don't know if you.
Yeah, I'll give you. Look, we have a separate system. It's called the Project MJP 2500W. W stands for wax. It prints a full wax parts for jewelry casting. It's the industry leading system. We've sold many thousands of the 2500W all across the world to all of the largest jewelry nodes, whether it's Dubai, India, Turkey, Italy. All of the main manufacturing nodes for jewelry are using the 2500W system. It's highly reliable. It's the same form size as the 2500 Plus that we've been describing today. And of course, the only difference is in the jetting of a wax suitable for wax casting. We also have a figure 4, a resin-based jewelry system called figure 4 jewelry. That provides 2 materials with 3 workflows. So you have a resin for jewelry investment casting, and then you have a high temperature material used for silicon molding, master patterns in jewelry, and also prototyping, try-ons, and stone setting. So we have 3 workflows covered by 2 materials on the figure 4, but we have the wax on the 2500W system.
Yeah, I would add to that we've got a number of 2500W systems out in the field here in Australia, and I know that the largest jewelry casting house in Australia are running multiple of those of that platform. So it's certainly industry leading here in Australia also. So please get in touch with us if you want more information around the 2500W. That is all the questions covered. So I would say, firstly, thank you, Sam, for your presentation. Brilliant once again. Thank you, everybody, for joining us. Keep your eye out for follow-up emails. We've got plenty more information on our website and more webinars coming up in the coming weeks. So thank you very much for your attention this afternoon and joining us. Have a great day.
Giving shape to ideas. Konica Minolta.